refrigerator and heat pump. So that combinations are there, right? So the heat transfer to the heat engine is 2000, and the net work output of the combined engine refrigerator plant is 360, right? So out of which the combined, so this is the combined, that combined is, it is going to give the 360 kilojoules, 360 kilojoules, but out of which one is considered as a W1 and the another one is considered as a W2. One is considered as a W1 and another one is considered as a W2, right? So this is the first thing, you have to draw the diagrammatic sketch. This is what the diagrammatic sketch is to be drawn. So if you remove this particular barrier, then this is here, you connect it to this one, so that 40 degrees centigrade. Now the refrigerator is operating between the, for this particular case, and if you just observe the refrigerator, how you are going to draw this one. So individually, if you just observe the refrigerator, this is the source and a refrigerator operating between the source and the sink temperature, right? So here work input is given, and observe the directions for this one and observe the directions for this one. This is the Q2, this is the Q1, just opposite of the heat engine operation. So this is the W, opposite of the heat engine. So here it is considered as a source, here it is considered as a sink. Sink is nothing but freezer. Sink is nothing but freezer or low temperature compartment. Sink is nothing but the low temperature compartment. Source is nothing but the high temperature compartment. Source is nothing but high temperature compartment. Now you come to here for the refrigerator. This is the sink and this is the source. This is the sink, right? So for this case, this particular point, it is going to come as sink, right? So you here from the sink it is taking out, right? So from the sink it is taken out, and this is nothing but source. So for this case, it is going to come as source, right? Now here what you have to do, so first thing is evaluating the system. So here observe that the first point what you have to find out is, find out the efficiency, maximum efficiency from the heat engine. So the maximum efficiency from the heat engine, what you will get is 1 minus T2 by T1. You come here, 1 minus T2 by T1. So that is 1 minus T2 is 313. What is the T1? T1 is 873. So the efficiency, what you will get is 0.642. 0.642. Efficiency is 0.642. Then what is the maximum efficiency? This maximum efficiency is nothing but network divided by heat supplied. Network divided by heat supplied. Network divided by heat supplied. So that network here I will call upon, that is the W1 by Q1. You come here. That network is nothing but W1 divided by Q1. So already Q1 is given. So this Q1 is, what is that? 2000 kilojoules. Q1 is 2000 kilojoules. So therefore W1 you will get it as 1284 kilojoules. 1284. So after calculating this one, then you will get it as a 1284 from this particular point. Clear? So that is this is how the heat engine is there. So this particular portion is over. Now come to the second portion. So I'm erasing this part. Come to the second portion, that is the COP of a refrigerator. COP of a refrigerator. So what is the COP of a refrigerator? The COP of a refrigerator, the COP of a refrigerator, COP of a refrigerator, which one is the desired effect here? COP of a maximum refrigeration cycle. Maximum refrigeration cycle. So that is here, this is the desired point. This is the desired point. That means the low temperature divided by the high temperature minus low temperature, right? Low temperature minus high temperature minus low temperature, because the refrigerator has to operate, because this is the desired effect divided by W net. So TL, or here you can consider it as a T4 for this case. So it is T4 divided by T3 minus T4. So T4 divided by W net, that is nothing but W2. So T4 divided by W2. Then what is the coefficient of performance? TL is 253 divided by 313 minus 253. So what you will get? COP you will get it as 4.22. COP you will get as 4.22. But what is this? What is this COP? What is this COP? This COP is nothing but equal to Q4 W divided by W2. Q4 divided by W2. Q4 divided by W2. But we know that here, see here, now you come to this particular side. So we know that W is nothing but equal to, and it is coming in this one, and it is, see, W is equal to W1 minus W2. What is W here? It is 360. It is 360. W1 you have got it as W1 you have got it as 1284 minus W2. So W2 is equal to, you will get that W2 as 924 kilojoules. You will get W2 as 924 kilojoules. Clear? So from this case, this W net is equal to W1 minus W2. This is the work output, and here W2 is nothing but work input to the refrigerator. W1 is the work output from the heat engine, but the combined engine is going to produce the net work output is this one, right? Clear? So this is this is how the problem is connected to it. So once after getting this W1, W2 and W, then you can easily sort out, or you can easily make the calculations of this Q4 and Q3. So try to come to that particular place. So I'm going to erase this particular point. So because keeping the diagrammatic sketch is very important, then you can easily approach, you can solve the numerical problems to this particular side. So then what happens here, once this COP is here, you come to this portion, right? So the COP of a refrigerator is equal to Q4 divided by W2. What is the COP of a refrigerator? You have got it as 4.22. That is equal to Q4 you have to find out, and W2, this W2 you have got it as 924. W2, it is that is after observing that one, 924 you will get. So from this case you will get it as a Q4. So the Q4 value you will get it as 3899 kilojoule. 3899 kilojoule. right? So now this value you have got as 3899 kilojoules. So try to observe how you are going to getting the Q1, Q2, Q3, Q4. This is of importance. That is, this is of requirement for making the calculation. So once this Q4 you have got, then you can easily get this Q3. Then here Q3 is nothing but equal to W2 plus Q4. So what is this W2? That W2 is 924, 924, and Q4 is 3899, 3899. So you will get that Q3 value as 4823, 4823 kilojoules, 4823 kilojoules. Then come to here, that is here, you know the W1, you know the Q1 value, right? So this W1 is equal to Q1 minus Q2. W1 is equal to Q1 minus Q2. So with this one, Q2 you can get. So that Q2 value is 716, 716 kilojoule. Already we know that that W1 is 1284. So that is earlier you have made the calculation 1284 kilojoules, right? 1284 kilojoules. So now you know the values of all the source temperatures and all the heat transfer, that is Q1, Q2, Q3, Q4, right? So now what you have to do, evaluate the heat transfer to the refrigerant, evaluate the heat transfer to the refrigerant and the net heat transfer to the reservoir, and the net heat transfer to the reservoir. Net heat transfer to the reservoir at 40. So the reservoir at 40 means this one. So for that case, what are the things are connected? So for that case, these things are connected. That is heat rejection. So for this case, then what you are going to get? It is Q2 plus Q3. So the total heat rejection, total heat rejection, that is the total heat rejection to the reservoir is total heat rejection to the reservoir at 40 degrees centigrade, or total heat rejection to the this particular reservoir, that is 40 degrees centigrade, that is equal to Q2 plus Q3. What is Q2 and what is Q3? That is after making the calculation, that is already is given. So 5539, 5539 kilojoules, 5539 kilojoules. So this is the answer. Hope these particular things are clear. Now what is going to happen here? In the second bit, what is given? So these are I'm going to erase this portion. In the second portion, what is mentioned? Given the efficiency of a heat engine, given the efficiency of a heat engine, and the COP of the refrigerator are 40% of their maximum possible values. 40% of their maximum possible values. So what it is given? So that means earlier whatever the value you have got, that is the COP of a refrigerator is equal to, that is the second bit B bit, given that the efficiency of a heat engine and the COP of a refrigerator are 40% of their maximum possible value. So 40% means 0.40. The earlier value, it is 4.22. Earlier value it is, so this is the earlier value, coefficient of performance of a refrigerator, and here it is the actual is equal to 0.44 of 0.40 times, that is into 4.22. So this is what the earlier calculation. What is this particular actual, that is this particular point is nothing but equal to Q4 divided by W2, that is equal to 1.69, 1.69. So with this particular calculation, where you can get the Q4 value as 259, it is 259.6 kilojoules, right? 215.6 kilojoules. Now, once Q4 you got, then what is this Q3? Then Q3 is equal to W2, right? So here you will get the W2, right? So W2 plus Q4. So if you solve this Q3 value, then you will get it as a 413 because this Q4 is nothing but this value 413.2 kilojoule. 413.2 kilojoule. So in the same way, correspondingly, here you can get the Q2 value also, right? So that Q2 value, it is because the efficiency is also to be considered. Here the efficiency. So let me write that efficiency also. So the efficiency of a heat engine is equal to 40% of the earlier case of a heat engine. So try to solve that one and you will get the Q2 value, and finally all these things are there. So that is from the second bit, that is 40% of their maximum possible values. The heat rejection here, evaluate the heat transfer to the refrigerant, and so that means the Q2 and Q3. Q2 and Q3 when you consider 40%. So the answer here it is 1899. 1899.6 kilojoules. 1899.6 kilojoules. Right? So this is how you have to solve the numerical problems connected to this point. Hope this particular thing is though the problem is lengthy, but if you analyze the procedure of making the calculation of these particular cases, then these things are very easy. Just only thing is analysis, that is the the solving the problem analysis, right? So a mechanical engineering student has to develop the real societal system mechanical problems analysis. See how the refrigerator is performing its best at the atmospheric state conditions. So all these evaluations are connected to this particular site. So this is one problem. Next one. This is also the problem is lengthy, but it is very easy. But it is so here it is proposed that a solar energy this can be used. Solar energy this can be used to warm a large refrigerator. So to warm a large collector plate. Proposed that a solar energy be used to warm a large collector. So in the overview of a lecture, I also discussed that the thermodynamics is going to play an important role in the solar energy system. So now connecting to that particular point, so a large collector plate. This energy would in turn be transferred as a heat to the fluid within a heat engine, and the engine would reject the energy as the heat to the atmosphere. So experiments indicate that about 1880 kilojoule per meter square hour of energy can be collected when the plate is operating at 90 degrees centigrade. Estimate the minimum collector area that would be required for a plant producing 1 kilowatt of useful power. Right? So the atmospheric may be assumed as this one. So this is the problem. Very simple thing is there, right? So only thing is that what is the maximum efficiency, because here all the temperatures are mentioned. All the temperatures are mentioned. So what is the maximum efficiency? Because it is the heat engine is mentioned. So generally we all know that the maximum efficiency is 1 minus T2 by T1. So that is equal to just the problem is lengthy. That's all. The solution is very simple. 1 minus What is the T2? It is assumed the atmospheric temperature, that is 293, 273 plus 20, 273. Next, another one is the 90. So 90 plus 273, it is 363. The efficiency is 0.192. Efficiency is 0.192. But what is this maximum efficiency? What is this maximum efficiency? That maximum efficiency is nothing but equal to W net divided by minimum heat input supply. So minimum heat input supply, see here, R W divided by Q1, minimum heat input supply, right? So for this case, what is that is a plant, the collector area that would be required for a plant producing 1 kilowatt of useful work output. So that means this is 1 divided by Q1 is equal to 0.192. So with this one, what you are going to get to the Q1 value is 18,800 kilojoule, 18,800 kilojoule per hour, 18,800 kilojoule per hour. But your aim is to find out estimate the minimum collector area. Estimate the minimum collector area. So estimate the minimum collector area. How you are going to get? There is experiments indicate that 1880 kilojoule per meter square hour. Meter square hour. So how you are going to get the area? So that area is nothing but through the units you come out. Through the units you come out. So if I do like this one, that is 18,800 kilojoule per hour divided by this 1880 kilojoule per meter square hour. Meter square hour. Kilojoule. So kilojoule hour, this is cancelled. So only you will get it as a meter square. So that is equal to, you will get it as 10 meter square. That's all. 10 meter square. So this is the problems. Maybe sometimes the problem is lengthy, and solving that particular problems are very easy after understanding the heat engine concept, and how you can connect that heat engine concept to the solar energy systems, so that you can solve the problems very easily. You can solve the problems very easily. So this is one problem. Next one is a domestic freezer. So the domestic food freezer maintains a temperature of minus 12 degrees centigrade. See how all the problems are connected to the in day-to-day life. The thermodynamic problems are connected, how these thermodynamic problems are connected to the day-to-day situation. A domestic food refrigerator maintains a temperature of minus 12 degrees centigrade. The ambient air is 35 degrees centigrade. Heat leaks into the freezer at the continuous rate of 2 kilojoule per second. Determine the least power necessary to pump this heat continuously. This is what the theoretical concepts what we have learned. So try to draw the diagrammatic sketch. So draw the diagrammatic sketch. Now what you are going to get? So that is here minus this is 35 plus 273. So the 35 plus 273, it is 308 Kelvin, and the another one is food freezer minus 12 plus 273. You will get it as 261 kelvins, right? So this is nothing but the freezer, food freezer, or food refrigerator, food freezer or evaporator compartment. So the directions reversed, right? The directions are reversed. So this is Q1 and this is Q2, and here giving the work input. This is the refrigerator. This is the refrigerator. So here the least power necessary to pump the heat out continuously. So the important issue which you have to observe, that is